Namaskar,
Yeah,
Kundu
good
sir.
morning. Good morning.
Okay, good morning all. I heartily welcome Dr. Prasanta Kundu sir. Uh, Before we start our session, let me introduce our expert. Dr. Prasanta Kundu sir received B degree in electrical engineering from BE College, Shibpur in 1992 and ME degree in electrical engineering with specialization in high voltage engineering from the Indian Institute of Science, Bangalore in 1994. PhD degree in electrical engineering from IIT Kharagpur in 2009. He is working as associate professor in electrical department SVNIT Surat. He is the recipient of 2007 IEEE DEIS Graduate Student Fellowship. His area of research is condition monitoring, application of DSP techniques, electromagnetic field computation. He is associate member of the Institution of Engineers, India. He has published around 100 research papers at various national and international journals and conferences. Today, he is going to deliver an expert talk on condition monitoring of transformer. Now, I would like to hand over this session Dr. Kundu sir. Thank you.
Yeah, thank you. Good morning, all.
Good morning, sir.
Myself,
Good morning, sir.
myself, Prasant Kundu. I will talk related to the condition monitoring of transformer. So, for this regard, I will have a PPT. I will just share that one, and with that, I will going to talk. Condition monitoring of transformer. Here you can have two basic words over here. One is condition monitoring. Now, condition monitoring, another one is the transformer. So, transformer is a device of or system or electrical engineering. Now, why to do the condition monitoring? There are many techniques for condition monitoring. Just to understand or appreciate that approach of condition monitoring of it, I normally give a very common example before starting the appreciating what is condition monitoring going to do it. This is just like a checking of the human health. We go for the blood pressure checking, sugar checking, and so many medical tests we used to do it just to understand what is the status of that one. And you know it, if you go for testing of that one, that doesn't improve our health unless and until you take some precautionary measure from the diagnosis, from that test. This is the same thing over here in case of any electrical equipment, including transformer. We do certain type of test to understand the condition or status of that particular equipment before going for any major failure. So that once we understand that there is a certain problem, we can take a precautionary measure before having to the fault is extended to a very significant value, where it is very difficult to come back, very difficult to repair, or there is a unwanted downtime. If certain equipment fail suddenly, pre-planned, then also there could have some problem. So if you check the condition of the equipment, if you can predict it that yes, it is going to fail within few months, then we can do certain precaution, means we can have some standby transformer, we can do a repair, we can arrange it, we can have a minimum losses. So there are many techniques of condition monitoring, but I will specific only these two techniques, that is the partial discharge measurement. This is normally done in a case of transformer and sweep frequency response analysis. These are also the part of a condition monitoring of transformer. But I will tell you that there are many techniques related to condition monitoring, specifically for a transformer. But these two are very major ones. We will understand these two techniques one by one. So first we will talk about the partial discharge measurement. Partial discharge measurement is also, partial discharge is also abbreviated as a PD. It is very well known in a high voltage community. It's a partial discharge is well known as a PD. Partial discharge means stand for PD, stands for the partial discharge. Now, why to do the condition monitoring, which is true for, it should have a reliable operation, that it should not have unwanted downtime, and so condition based maintenance also normally used to do it by condition monitoring technique. Condition based maintenance. Condition based maintenance means there are two ways we normally do the maintenance. One is the time based maintenance. Means without knowing the condition or status of the equipment, after few months, after few years, you do it, that maintenance. That today if you do one equipment maintenance, that will have a tag card, then after 6 months or after 1 year, whatever be the time schedule, based on that it will be done. But we don't check it, that either after 1 year it is really needed to do the condition maintenance, or before it is having something we should do it before that. And so that's why instead of going for time based maintenance, condition monitoring is also used for the condition based maintenance. There are different techniques for the, specifically for the transformer: dissolved gas analysis, Herefeld diode analysis, degree of polymerization, partial discharge, capacitance and tan delta, frequency response analysis, recovery voltage measurement, current measurement, vibration measurement. All these are done for the condition monitoring of this equipment. And this can be done online as well as offline. Online means equipment is connected in the site itself. We don't have to switch off the supply. You don't have to take the equipment out of the circuit. You can on state. So that is more advantage because you don't have to interrupt the supply. So online condition monitoring can also be done, and offline, that is necessary in some situations where you cannot do or cannot diagnose it properly in online cases. So then offline is done. So that time you have to switch off the supply, you have to take out the equipment. So after taking out the equipment, there can be done 2-3 different like on site. After taking out it, but there itself, in the site itself, because transformer may be installed at some particular place, so you don't have to bring it to the factory again or in a laboratory again. So there itself can be done, but not in online, offline, but on site. But online can be done on site only. No, that is natural, that you have to do online directly on the on site. Offline can be done on site. Some tests cannot be done in the on site, so you have to bring it to the factory or laboratory. That laboratory and quasi laboratory, which is the factory, is dependent on the noise level of the environment. That both are in the out. You have to bring it to some locations. The two difference of this one is laboratory and quasi laboratory based on the ambient noises. In case of laboratory, ambient noise will be lower. In case of quasi laboratory, ambient noise will be higher. Again, that test which is more prone to or sensitive to the noise, you cannot do in a quasi laboratory cases also. You have to go to the laboratory situation where the noise level is low. Now, partial discharge. In partial discharge, we will talk a little bit of the fundamentals. Those having the high voltage engineering background or at least studied high voltage engineering subjects will have the knowledge of this one. So for them, some part will be repetition. So I will move quickly. We will have fundamentals a little bit about the partial discharges because some of them may not be aware of the PD. So as for sake of completeness, I have given a little bit about the fundamentals of partial discharge also. Then we will talk about the basic 3 methods of PD measurement: electrical method, acoustic method, and UHF method. So in basics of partial discharge is a localized electrical discharge that only partially bridges the insulations between conductors and which may or may not occur adjacent to the conductor. It is partially bridges the conductor. So this is a figure in the next of it that you can say that it is just a schematic of a cable. So inside this is a conductor and outer sheath. So there will be some void over here in the insulation that can come because of the manufacturing defects or because of the operations, because of the heating cycle. So in that void, there may have some discharges. So this discharges is not bridging. So there is a two conductor. One is at a higher voltage, another is lower voltage, that is the ground. So the two conductor are not connected directly to the discharges. That is the meaning of the partially bridge. Bridge means it will connect this one conductor to the another conductor. So that is the full discharge. But here partial discharge. So it may be connected to one of the conductor or may not be connected to any of the conductor. Either it may be connected to the high voltage conductor or may be connected to the ground, that is the low voltage, zero voltage conductor. So it may adjacent to the any conductor, may not be adjacent to the another of the conductor. So what is the problem over here? Because of the discharge, this discharge magnitude is very, very small. Because of the discharge, transformer or any electrical equipment will not fail immediately, but it will going to degrade the insulation. So this discharge is a small arcing. It will have a heat, light, sound. So that will just erode that insulation slowly, and slowly this gap or this void will increase and it will going to create a final failure. So that is the insulation degradation. So there are many techniques to measurement the PD: electrical, optical, optoacoustic, ultra high frequency acoustic. And out of these different techniques, some of them are online, some of them are offline. So in a defects of insulation, this is showing the how the defects insulation is modeled. So upper one is a copper conductor, then iron core. In case of transformer, you can model it, and there will be insulation in between the copper conductor and the core. So the void can occur adjacent to the copper conductor toward the conductor side or in between of it, neither touch to the copper conductor, neither the core, or it may touch to the iron core. So that may have a void in any higher over here, and in any positions discharge may start. So based on the different position, discharges, partial discharges are classified in the different eye. So one part is if it is connected to the sharp point, this partial discharge in the point plane cases, it can have a surface discharges in the surface of the insulation on the conductor, or it can have a internal discharge that is inside the void. This discharges when it is connected to the surface of the conductor, and the most of the part is other insulation that we also refer as a corona discharges. That is happening in the HV, EHV, or HV transmission line. So same thing will happen over here. So any sharp point will create a discharges. Now how discharge is going to occur? Why discharge is going to occur inside that void? So that can be explained with the help of this ABC model. So I told you that if there is a void, any point of the conductor, it can be modeled like this ABC diagram. So this ABC diagram is a very common diagram for the partial discharge community. So for explaining the partial discharge phenomenon, what's happening for that? I will refer one diagram over here, so which I have drawn it. Instead of going back to that one, this is the same part. I'm drawing it over here. Same part, I'm drawing it over here. So what this ABC model is done, so we're going to tell it quickly, so that say this is the insulation block. This is the insulation block. There is a conductor apart to this one. There is a conductor lower to this one. Say this is the high voltage conductor. This is the ground conductor, and say there is a void at any point of it, this is the void. It may be touched to the hv conductor, it may be touched to the ground conductor, or it may be in between of it. So in these cases what is done, this total insulations is part into three segment A, B, C. I have marked this one. This is the insulations. Now one part is in, this is still insulation, this is only the void. So some will be, so you can check three part. One is the void. Another one is the series with the void in this side as well as in this side. These two sides, this side as well as this side. This is the series with the void. And another part is the parallel, this side as well as this side. So you can have a three capacitance. This void capacitance is denoted as a capacitance C, which is in series with this void, this healthy insulation, that total, this part, both the side, that is denoted as a B, and which is in parallel with this one, other than this part, this side as well as this side, that is denoted as a capacitance of that is denoted as a A. So that's why you can have a model of A, B, C, and that A, we have drawn that ABC model. ABC model is drawn in this particular way. There is a two path, 1 and 2, A, B, C, and C is the representing the void, that is representing by this gap in this diagram. Okay, so whenever this voltage will be applied, supply voltage will appear across the insulation, across the total insulation. So this will going to divide according to the capacitance. If two capacitors are connected in series, based on the capacitance value, voltage will be divided. So some voltage will come across C, some voltage will come across B, depending on the, and this is the A. We can have the, as soon as the voltage across the capacitance C, that is the voltage across the void, is exceeding the breakdown voltage of that void, so that gap will break and you're going to have a discharge. So this is the voltage across the gap C, this is the supply voltage, and rest of the part is the voltage of the across the B. So VC plus VB will be the VA, this total voltage. VA is the total capacitance, full voltage will appear across the capacitance A. So, and once there is a discharge, this voltage will fall to 0, and again it will start recharging, and again it will repeat. So that is reflected as a different pulses in the circuit. So this way it is measured it. So this reflected in the circuit, which is put as a coupling capacitor, and test object capacitance, it's a quarter pole. This is measured in a PD measurement instrument or in a oscilloscope. So this discharge pulses will have three components we can measure it. One is the phase angle, number of pulses, and magnitude of that pulses, which is called the phase angle of the pulses phi, number of pulses n, and magnitude of the pulses q. That is normally represented in the chart. It is normally PD unit is picocoulomb. In some situation they put in the millivolt also in case of a rotating machine, but maximum cases we go for the picocoulomb. So phi q again, so that is been put it over here. So phase is phi, count is n, and q is the magnitude, amplitude. So that way you can have a phase resolved PD pattern, and that gives the nature of the PD and nature of the degradation. So this part is, this axis is phi, this axis is q, and this axis is n. So count, number of pulses n. So this is the phi qn pattern. So this is the phase resolved PD analysis after routing it. So there will be PD measurement instrument, and even normal oscilloscope also can be used to measure the PD. But for that some more analysis is to be done, but you can have a dedicated PD measurement instrument. Now In the present trend, specifically for the HVDC applications, here you will find out some transformer is subjected to both AC as well as DC voltage, specifically the converter transformer. So there, PD can be characterized using the AC-DC voltages also. So this is the one zone of the research that specifically for the converter transformer. If you are measuring the PD using the AC, and if you add the DC on it, the nature of the PD is going to be different. So here you can see that sample is given a AC supply from right side and DC supply from left side together, and this AC-DC's combined test is conducted to check this one. So there is a certain order of it. So DC is first applied. This is the application of the DC is initially applied, keep constant. Then AC is applied on it. So AC will be superposed on it. You can have a higher value of DC magnitude, lower value of AC magnitude, and based on that, you're going to have a resultant of it. Now, here, and we will have a DC voltage. This is a few result from research article. So the PDIV is how the partial discharge. PDIV means the percentage insertion voltage at which voltage partial discharge will start. Right. So that voltage can be used to understand the partial discharge characteristics. So here, in some cases, irrespective of the DC voltages, PD inception voltages, partial discharge inception voltages, PDIV is constant. Some cases it is increasing. So there is a different pattern for the different cases. So this is just for reference. Now we go for the acoustic partial discharge detections. PD creates a noises. So here again one synonymous example can be given here. Discharges, electrical discharges or partial discharges. Partial discharges, smaller level partially is electrical discharges, but not full discharges. So, but it's very small level. Its magnitude is in picocoulomb. It's very small. It can create only few millivolt signal. So whenever there is a discharges, it will create some acoustic noise. So biggest discharges what you can have it in, that is the lightning discharges. Right? Lightning strike, the naturally what is happening from the cloud to sky, that is going to have a lightning discharge. So that is, you know, that is associated with a very high noise and high acoustic sound. So that sound is used to measure or characteristics the PD. So PD will create acoustic pressure pulses and it will propagate. So in this diagram, you can say that in this below of this second diagram, that PD is created a pulses, acoustic pressure pulses that will propagate. It is a sound wave is generated, pressure wave, sound wave is a pressure wave. So sound wave is generated and it will propagate based on the medium velocity to all the directions, and piezoelectric sensors which is put on the surface of or at any locations of the transformer, and piezoelectric sensor convert the pressure pulses to electrical signals and used for measuring and recording. So this acoustic partial discharge can be used for the source location, and it is immune to electromagnetic interference because it is a pressure pulses. So there is no point to it will be interfered with the electromagnetic noise. Sound wave is a pressure wave, electromagnetic wave cannot be interfered with. And it is a non-invasive. It can be connected, sensor can be connected outside the tank also. It can be used online and it can be used on-site. Since it is immune to electromagnetic interferences, it can be used online and on-site. So this is a typical diagram given for how the measurement is done. So here you can say, see this one, that this is transformer core, and here there is a gap is provided and the acoustic sensor. So this is a complete model of a transformer tank which is filled with the transformer oil, and there is a PD sources is created, and acoustic sensor is put. Acoustic sensor is put over here. So you can see in this case, this is sensor number 1, then sensor number 2, this sensor number 3, sensor number 4. Four sensors are created, and this is the source. This is the source of pulsar sensor. So they are connected. They are connected through this supply. This is high voltage source supply is going to, this is connected, and this is the combined electrical measurement. This circuit is having a combined electrical measurement, right? So this side is coupling capacitor and combined. So that is the one part. It is together electrical measurement. This is the electrical measurement component, and this side is the electrical component measurement, and this is the acoustic measurement. And sensor is goes to the acoustic emission measurement system or simply oscilloscope. Both the cases, oscilloscope is necessary, either electrical measurement or acoustic measurement. Little bit higher frequency band. Normally, frequency band of the PD is around 150 kilohertz, and little bit higher than that one. So you can have 100 kilohertz is alright to have a measurement of percentage, right? So this I just mark this one to understand how you have the source location algorithm. We will talk it. So that time the algorithm will be connected based on the sensor position. So each sensor can have its own coordinate system. So if you take a three-dimensional tank, each sensor will have its own coordinate system. The sensor 1, sensor 2 will have its own coordinate system. Sensor 3 and sensor 4 will have own coordinate system. So for example, sensor 1 is having a x1, y1, z1, because it will have a 3 dimensions. So you're going to have a 3 coordinate. Same way x2, sensor 2, sensor 3, sensor 4. And this is the source of PD. This is the source of PD. You cannot predict where it is going to occur. Right. So this is the source of, okay. So x, y, z, and this is x2, y2, z2. This will be x3, y3, and pulse will propagate all the direction. Right, since it is a two-dimensional diagram, so it looks like a two-dimensional, but you can imagine it is three-dimensional. So PD can generate a PD pulses. So you can have a pulses, acoustic PD pulses of this one. It can be frequency domain analysis can be done for it, and you can get a characteristics of this one. There is another way to analyze the partial discharge acoustic wave, that is the discrete ovulate transform, which is decomposed into different label. So discrete ovulate transform, you're going to have a selection of mother wavelet, selection of decomposition element, calculation of energy is decomposition element. Right, so this can have a two different run. You can have a different decomposition in the discrete wavelet. The PDAE signal can be analyzed. The direct transform also used to analyze the signal. So packet transform, you have two side of train. In case of discrete transform, only the approximate is being decomposed. Here both approximate and details are decomposed. It's going to have a different level of train. Now here partial discharge is going to create a different frequency band, but in case of transformer there is a sources of error in the different frequency. So what are the different frequency acoustic sound is possible in case of a transformer is given here. That is the electrical, you can say air corona, you can have this is substation. So there is so many other high voltage point in the circuit breaker, in the terminal connectors. So they all are creating the partial discharge or corona discharge. So that also creating an acoustic pulses. So that pulses inside that asthma pulses, if they are misunderstood, then what is going to happen? So now this frequency analysis can help you to understand what will be the different band of or different frequency range of the different type of discharges. So in case of A, it is normally 20 kilohertz to 5 megahertz is used, or but it may only 150 kilohertz resonant type also been used. So different frequency, corona is going to give it a little bit higher frequency, 24.4 megahertz. So it is very high. So vibration of the tank is also going to create a noise that is 2.5 kilohertz. Operating a cooling fan, that is also creating a acoustic or mechanical noise, that is 4 kilohertz. Then cooling pump, that which is circulating the oil, that is also creating a pressure pulses, so that is 2 kilohertz. So they having a different frequency. Cooling fan, that is in 2 kilohertz. OLTC operations is going to give 143 kilohertz. Whereas PD and OLTC operation seems to be the same zone. So, but that is done with a time analysis. While TC pulses, while TC operation pulses will have little bit wider durations, 100 milliseconds. Whereas PD will have a 20 to 30 milliseconds. So that can be identified. Now I told you that PDA is having the basic component of the source location. So source location, we're going to have the iterative algorithm can be ported its source to the different sensor, one y1 z1, the core sensor is core coordinate, and source if it is xyz coordinate, and the source to sensor distance is different, so it will take a different time to propagate, and based on that you're going to have a set of equations, and based after solving this 1 2 3 4 these equations, we can find out the location. Now we'll talk about the EHF monitoring. This is also one zone we are doing the working on this ultra high frequency PD detections. This is a schematic diagram. Some of the things are like the source location algorithm and other component is almost similar type acoustic, but it is a different. Meaning some part is different, some part is similar. Different in this side that it is not a Pesar pulses, but it is the electromagnetic wave. PD also generates some electromagnetic wave. So that electromagnetic wave is been captured by antenna. So this antenna, so from the source to the antenna also it will propagate. So that it will propagate at the speed of sound. Here it will propagate at the speed of wave or light. So that is different, but both are propagating. It will have a shorter time, it will be a longer time, but all the 4 sensor will going to have a 4 different time. So you can understand that is taking a longer time because it is this moving at a speed of light, and this is taking this will take a shorter time because it is moving speed of light, that is taking a longer time, that is moving at speed of sound. So based on that, you will have a time, will have a difference. So here the bandwidth will be for the UHF is 300 megahertz to 3 gigahertz, and it will have a few nanoseconds. There the delay will be around few milliseconds. Here it is nanosecond. It will be little bit faster, right? And here it is 300 megahertz. There it will be hardly you can have few kilohertz, and at the most 20 megahertz. So not that big. So that is going to what it. So in case of UHF also phase resolved PD can be done. Phase resolved PD means that 5QN pattern can also be done. You can understand this part if you go for a little bit further study, because I will not cover that one in details, but just for informations that UHF PD also can be used to go for the phase resolved PD analysis. So when we go to application to the UHF in power transformer, it has to put the sensors, but sensor is that antenna to capture the electromagnetic wave. But if the tank is a metal tank and PD is occurring inside the tank, so the tank will act as a Faraday cage. So it will not allow the PD pulses to come out. if you put the sensor outside. So that is the problem in this VHF, and that means the sensor has to be put inside the tank. Otherwise, tank will act as a Faraday cage. Electromagnetic wave will not come out from the inside where the PD is occurring. Or you can have a dielectric window. Instead of metal tank, you can have a dielectric window. Higher sensor. So dielectric window, wave, electromagnetic wave can pass through the dielectric, but not through the metal tank, not through the metal. Right. So that is also Faraday cage. That is having electromagnetic shielding principle. That is also altogether different. But here you can just have idea that metal tank, any, will not allow the magnetic wave, electromagnetic wave to come out. So that's why it's to be either there is two options: put the sensor internally or put a dielectric window. So location of PD is done by what we talked in the acoustic similar ray, but since they say that's why I didn't repeat that one. But there's another ray also can be done by the taking the time differences of even the two sensors. The multiple PD also can be located. The S1 and S2 is the sensor, and there is a many PD sources in a single transformer. Then by judging the time differences, it can be predicted how many PD sources is there. So this I can put it. The sensor 1 and sensor 2 is recorded this electromagnetic wave, which is captured in the antenna in the oscilloscope. So oscilloscope should be at least capable to capture at least 300 megahertz to some extent gigahertz. And two sensors will have different distance from the sources, and hence they will appear to sensor at a different time. So there will be a time differences. So this time differences is calculated to find out location. Now there are many types of sensor is normally used for UHF PDD. Straight wire, zigzag type, helix, conical, spherical antenna, right? So conical monopole antenna is basically we are using it, and it's giving a better sensitivity. We have tried the straight monopole helix also, but conical is giving better. So these are the details of the definitions of the different sensor, and I will go for the conical sensor. And it has been this one figure and photograph is given over here. Uh, it will have a just a shape of cone. It will going to have some base diameter and some of the axial height or length, right? So you can put it the length at what frequency you're going to measure. What should be the frequency of this one? If you go on increasing the diameter, you will have more and more sensitivity. This diameter is 2.5 centimeter. If you have 5 centimeter, you have more sensitivity. Sensitivity will go on increasing if you keep on increasing. But if you want to capture a different frequency, then the length will be different. Length will be different. Length is depend on the frequencies, right? So that a what should be the length? If, for example, speed is constant, speed is the speed of the light, so lambda will be different frequency. So based on that, how much should the length of the sensor is quoted. So this is a typical setup of lab for the measurement of PD using the EHF technique. And this is the typical signals of a different gap of EHF1. And this is after doing the FFT. There is a certain DC component also the measurement, but if we go for the higher and higher component, we can find out what is the PD signal magnitude. For the different gaps we go there, and different PD signals are captured. Now we'll go for the next part of it, that is the sweep frequency response analysis. Sweep frequency response analysis. Okay, so sweep frequency response analysis is normally done for a transformer. PD can be done for other cases also, other electrical equipment also, but sweep frequency response analysis is done for transformer. right? Uh, this is also a condition monitoring technique. Uh, it is offline technique. PD measurement can be done online or offline both. Acoustic and UHF can be done online. Electrical method has to be offline. Uh, SFRA is offline conditional technique to detect the winding and pole deformations. Now, how it is done? It can be done time base for the same transformer to different time, design base to transformer to different design or to different type. And normally sweeping is done from 20 hertz to 2 megahertz. So this is the comparison test. What is the type and design base? This is the comparison test. What is done over here? This is also called a signature analysis. Signature of a two transformer. Signature of a two transformer or same transformer at a different time, same transformer at two different phases, right? That is time base means. So today you do a SFRA frequency response of a transformer A. After some time, again the frequency response is measured of transformer A, and these two are compared. If these are the same, so initially it has been done say at the time of installation at the new stage, and this is done after a periodic times, after 1 year, after 6 months, whatever is decided. So that is a time-based comparison. So A transformer and A transformer after sometimes two same. So if these are same, then it will be understood that there is a no fault is generated. If this comparison is that these are different, then some fault is generated. So it is a comparison. So you must have a references. Type based is done. In this is transformer A and transformer B are of the same design, same manufacturer, same rating, and everything is same, but two different transformers. So it can be compared these two. The transformer A is taken, transformer B is taken if these two are compared. If you know the transformer A is healthy, then the transformer B's response is not same that of transformer A, then we call transformer B is not healthy. Or it can be called both that response are same, then it can be called healthy. So if there is a comparison, that details we will go to take it on next slide. Design based means transformer A will have A, B, C or RYB phase. Each phase is almost identical, not exactly, because you know as far as the core positions, center phase will be different than the two outer phases. Right? If it is a three-limb construction. Even in case of high-limb construction also, because it's we're going to have some parameter which we're going to learn it afterwards. So they're going to have a some comparison. Now, some theory related to the sweep frequency response analysis, if you're going to know, that sweep frequency response analysis is possible of these three passive components, basic components, resistor, capacitor, inductor, and their response with respect to frequency or AC signals is entirely three different. We know resistance is constant with respect to frequency at all frequency. If you neglect the small amount of skin effect that we are not considering over here, basic value of the resistance is almost constant here. We don't consider it minor skin effect of this particular part, right? So resistance is constant with respect to frequency. We know that. Capacitive reactances is inversely proportional to frequency. If we increase the frequency, capacitive reactance will decrease. And in case of inductive reactances, that is proportional to the frequency. If we increase the frequency, inductive reactance will increase. So you can say one is constant, one is inversely proportional, and one is proportional. So because of these three different I of responses of these three passive elements, it is possible to have it. If you take one circuit, and this is a graphic representations of the resistance, inductor, and capacitor responses. Resistance is constant at all frequencies same. Inductor is inductive reactances, reactance is increasing with the frequency, capacitive reactance is decreasing with the frequency. If you're going to have a combination of R, L, and C, any circuit we can thought of it is a combination. So the responses will be different for the different impedance will be different for the different frequency, and hence the response. So in the SFRA, sweep frequency response analysis, input voltage is given and you are going to get the output voltages. Input voltage is given, you are going to get the output voltages. At input voltage is given at a various frequency. Input voltage is given a frequency from 20 hertz to 22 megahertz, 2 megahertz, 20 hertz to 2 megahertz, sweeping at a different step. So output voltage, because the impedance will change, this impedance will going to have resistance, capacitance, and inductance. So impedance will change and hence the output will change. So that if you're going to take a 20 log 10 of this divided by this and 10 20, so this response is got in dB. So here a simple example is given, R, L, C, and input is given from minor changes, is not what is going to be, let's say some hertz to a some hundreds of hertz. So you can see that impedance is varying. Impedance is varying because of the frequency dependency. Resonant time and omega L on the omega C will be same. That time it will be the R will be dominating, right? So that is going to have a different part of it. Now, this is represented in a dB form, 20 log 10 of this one. So you can have a response like this. So this is simple analysis, but in case of winding, we'll have a much more complexity. In a transformer winding, we'll have much more complexity. It will going to have a series capacitance from turn to turn. It will have a shunt capacitance from turn to earth. It will have inductances in each turn, and each turns will also have the resistances. And this L and C depend on the geometry. Now, if there is a variation of this L and C, and hence the response will be different, and that's how you're going to find it out. So this is a typical diagram. You can say that each turn will going to have some capacitances from the turn to the core, and from turn to the turn, from turn to the tank, and each turns will going to have inductances and resistances, and that is going to have a complicated RLC circuit. So in real transformer, this is a is not even totally drawn. It is just to show a sample one. So it is real transformer, many inductances, many capacitances. It will be a complicated one. So that's will going to have the input HV side and output other side. You can have a different combination of RL and C, right? So when we do the SFRA testing, it is normally done at a lower voltages, but at sweeping frequency. It is around 20 volt. Lower voltages, even if transformer may be 132 kV, but the output voltage, because impedance is not going to change with respect to the voltage, right? Whatever voltage is going to apply it, so sensitivity of the equipment, measuring equipment should be also. That's the requirement that you should. So transformer is normally disconnected when it is offline one. Transformer should be normal service condition, assembled on oil field, means disconnected, but none of the component like bushing, all are to be at the place. Make connections as determined by the winding configuration. Please, phases not under test are usually left floating, and this can be done two-way, floating or short circuited. In case of open circuit test, is got the winding with other connections floating but disconnected. In the short circuit testings, part of HV winding are sorted together the LV connections without grounding. The neutral is not included in the sorting, so that can be done in the sorting. So both way can be done, open and short connection. So this is a typical schematic diagram, measurement of the circuit, that you can have input KDS. This is typically is given over here. This one input voltage is given, and other side response has been measured. You can see in the bottom diagram, one side voltage is given over here. It's normally 20 volt. Generator is having 0.2 to 20 volt, but it can have only 20. Sweeping is frequency is more important, not the level of the voltages. Sweeping frequency is more important, not the level of voltages. So this is connected in one terminal, and another terminal you are measuring it, and the ratio can be measured. So there's a 2-3 different circuit can be done in a start delta form. Either all terminal is open, all terminal gets sorted, whatever it can be connected. In open circuit situations, we going to have the core branches, core side, you know the equivalent circuit of a transformer, this LV winding, HV winding, and the magnetizing branches. So in case open circuit test, magnetizing branches is normally get tested. In short circuit tests, that is sorted, until leakage component, the total winding is get tested. Right, so winding frequency response, winding have a frequency dependent response for transmitted signal. The detailed form of the frequency response depend on the winding geometry. A change in geometry will change the frequency responses, and that geometry change will going to occur because of some fault. Otherwise, there is no reason to change the geometry in between of operation. Right, that is the initiation of fault. That I am going to have a changes in the frequency by winding caused by the winding movement, and then we can detect the winding. Right, so that is, so there is a two different responses. Two different responses is given over here. Two different responses is given over here. That is one at healthy condition, another one is that different conditions. So you can see there is a variations of these two responses, and that can have a chances of failure. So we will interpret this one. There is a low frequency zone, lower frequency zone, and the high frequency zone. How we can going to have the interpretation of this one. So this is during the short circuit conditions. Same rollover, it is going to have a no variation. Right, so these variations between the, so this is why it is called the signature analysis. That's why it is called the signature analysis. That means once whatever response is given a transformer, and every time same response it should give, unless and until there is a fault, there is a deformation, so that it has been compared. Now in one frequency you cannot check it because of the fault nature will be different, and different zone will create a different frequency going to have a different. So that's why this is basically for the winding deformation, winding to ground deformations, and turn to turn deformation, turn to turn fault is indicated, turn to ground fault is indicated. Right, so this is going to have, it's basically this mechanical variations is been detected by some electrical parameter measurement. Open circuit response dominated by core at low frequency as with exciting current. Open circuit by setup is that LV winding is left out open. If you're doing the HV side, if you're doing the HV side, other winding is left out open. Other winding is left out open. So different magnetic paths lead to different responses, typically outer and center phase variation. So there can have a possibility because of the magnetic circuit of the outer two phases and the center phases are different, and hence this can have a minor differences. Short circuit effect in the lower frequency zone is normally removed. Short circuit in magnetizing part is normally not that much predominant. Short circuit, since the core component is been removed, so all the response would be identical. So whatever is that variation is that, it is because of the winding impedances. Center phase is treated separately. Now there is some sources of error in case of sweep frequency response analysis. If the core is magnetized before starting two comparison tests, so one as without magnetizations, another one is with magnetization, so there we are going to have a variation. But that is not the fault of the transformer, it is because of the core magnetization. So core magnetizing effect can come in the lower frequency. Now these are the different zone is used to identify the different type of fault. 4 zone is been classified because it is from 20 hertz to 2 megahertz. So first zone is less than 10 kilohertz. So here core deformations, open circuits, short turns, and residual magnetisms will be shown. If there is a variations in the zone from 20 hertz to 10 kilohertz, these are the possible fault. Now 10 kilohertz to 150 kilohertz another zone, that is the bulk of the earnings. This is experience based or based on the many number of tests it has been documented. Bulk winding fault, movement of the relative to each other, and clamping of the structure. So this will be the this zone. Then 150 kilohertz to 400 kilohertz deformations with the main and tap windings, and 400 kilohertz to 2 megahertz movement of the main and tap windings. Now there is some work is done with a 5 zone also, right? We did it few works related to the frequency response analysis. Core deformations and high impedance turn-to-turn faults is detected in this zone. Core laminations, open circuit turn-to-turn fault is detected next zone, and winding deformations, movement of the clamping structure is detected over here. Main winding or tap winding structure is done over here. Movement of main or tap winding is done in this particular part. Now here what I want to tell it that these are all the visual inspection you can check it. You just look at the two waveform, whether they are exactly matching it or they are not matching it, that you can have it. But if a cases is there, if there is a cases that say these two are there is a minor variation, but now if there is a situations that there is instead of this, if there is a cases, say this is coming out to be somewhere over here, variation but in this zone, but there is a major variation. So how to identify that one? Because if there is a minor variation, somebody will say it is because of not proper, it is can be acceptable if there is a not a minor major variation. So minor variation may be doubt. So for that there is a few parameters calculated, that is called the cross correlation coefficient. In each zone, whatever is been signified, each zone, a statistical parameter of the signal processing parameter, cross correlation coefficient is calculated. If the cross correlation coefficient of that particular zone is 0.8 to 1, then we call it is there is no major variation, means that is good condition. If 0.96 to 0.97, there is a marginal variation. If there is a less than 0.96, the cross correlation coefficient, then it has to be investigated. Then there is a problem of this transformer. There is a problem of this transformer. So then we are going to further evaluation. Now here in the different zone for the different type of fault is created, and how the cross correlation coefficient CCF cross correlation coefficient is varied. That is been checked it. So it is intentionally, it is just a model transformer, a model winding, we took it and did it. So there is a possibility if you're going to check it, and that will going to tell that at which zone which type of fault is going to occur. Now influence of core and voltages. Residual magnetism in the core will affect SFRA open measurement because the core is break in open circuit test, try to minimize the effect of however some difference may occur, which we accept. Make sure the transformer code is not magnetized. Perform SFRE measurement prior to ending resistance measurement or demagnetize the core prior to the SFRE measurement. So if a SFRE measurement, it has to be demagnetized to start it. SFRE open circuit measurement, magnetization impedance and voltage dependent. The same measurement voltage in all SFRE measures. So this is the minor voltage dependency of the code. So if there is the effect of magnetization, so there will be change in the load voltage. So you're going to have a demagnetizations, you're going to have a different effect. So voltage effect is also been possible to see it if you're going to do it at 10 volt, if you're going to do it 2 volt, if you're going to do it 5 volt, that can have a minor variations because so normally for this one it's the same voltage is done to user, but it is, you see, it is only volt. Transformer maybe a 132 kV, but it is done it in a volt. Now, oil level in transformer bushing also to be fitted at a proper place. With oil level and without oil also going to have a different variation. Basically, this one is that all the L and C, the transformer turn to core, turn to turn capacitances, turn to turn capacitances, turn to ground, turn to core capacitances. This all are depend on this oil. If you don't have the, because they are having the oil and without oil, you're going to have a different permittivity. So this capacitance will going to change. So as the different capacitance, and hence is natural to have a different responses, right? So that also to be checked. It should have at the same condition, right? So it is a comparison method. Uh, it is a comparison method, and you should have a reference response for this measurement, and reference response may be taken from the sister unit or the same unit if it is not possible. It is best one is from the same unit. If it is not available, then sister unit of the similar design. Still it is not available, then FEM simulations and modeling can be used to get the responses. Right, so this is related to the PD measurement and SFRA measurement. And now if you have any question, you can put it. I told you there are many other way of doing the uh, many other way also doing the uh, transfer condition monitoring. These are few of these things are related to. I will now,
Prof, session is on.
yeah, uh, few of these are related to recovery voltage measurement. Now we're going to share one board to tell you about that measurement.
Sir, Kundu sir, actually your screen is not visible. Share screen. I think it
Yeah,
will
just
be.
a minute. It's
Huh,
loading.
okay, okay, sir.
Yeah, slowly it is loading. Just
Okay, okay, sir.
please not. Okay, just a minute.
Yeah.
Yeah, just a minute. I will share this one. Yeah. Now, is it visible on whiteboard?
Uh, yes, sir, it is visible.
Yeah. So now I will tell some other component of the monitoring, that is the dissolved gas analysis. In case of transformer, which is going to have a hydrocarbon oil. So, and there is a partial discharges, arcing, anything. So this is going to decompose into a lower order hydrocarbon gases. So, or hydrogen gases, or it can be oxidized, it can create with the paper. These are the gases is created by the different temperatures. So dissolved gas analysis is also done to monitor the transformer. Dissolved gas analysis is also done to monitor the transformer, arcing and partial discharges. Dissolved gas analysis, this higher order hydrocarbon oil will decompose into the lower order hydrocarbon gases. Now there is a two part of it. One of the dissolved gas analysis is the key gas analysis method, and another is one is the ratio method. Some cases, if the transformer oil is full of gas, dissolved gas is a bit of different than the gas which is generated and which is monitored by the Buchel relay. It is not coming out from this one. So with this gas, its side itself it will be dissolved on that oil itself. So there, if some sample is taken and it goes to the dissolved gas analyzer and it is found how much is the lower order hydrocarbon gases is available, and after some time again if it is checked it, so one is the key gas methods, it is find it out how much is the gases. The problem of this key gas method is that if one day one fault is initiated and because of that some component of some gases has increased, some component of some gases is increased, now this fault is being rectified, this fault is being rectified, this gas, the total transformer oil is not done degassing. This sample only is taken. So after some time again, if you taste this dissolved gas analysis, this same gas will be found out. So instead of, so this is the drawback of the key gas method. So you can have a ratio method. Means two key gas ratio is being checked. What is the variation of these two? If today this is some percentage of this is there, this some percentage this is there, then because of one fault this will going to have a variation, this is going to not going to have any effect, then this will remain constant. So by that way also dissolved gas analysis used by the either key gas method or by ratio method to find out the condition of transfer. Second test related to this dissolved gas analysis is related to the continuous transfer is the degree of polymerization. Degree of polymerization. Degree of polymerization. The transformer there will be some paper insulation. It is cellulose paper, transport paper insulation. Now, when the paper is a new conditions, it is going to have a certain value of tensile strength. It is going to have a certain value of tensile strength, as or certain value of mechanical strengths. As it is going to have a aging, so this mechanical strength will going to reduces. So this is a polymeric paper, cellulose insulating material. So because of this one, this paper will going to have a brittle or it will going to have a lower mechanical strength. So that day also condition of the paper and the condition of the insulations is been identified. So degree of polymerizations. So it is just to check the mechanical strength of that paper. Mechanical strength of this paper. Next, there is a technique of the condition monitoring of a transformer is the recovery voltage measurement. Recovery voltage measurement, and this is quite a similar like a polarization, though but quite similar, not exactly same, polarization and depolarization current measurement. So in these cases, what is done, the transformer is initially charged with a DC voltage for some time. Transformer is completed, taking an example, and after that it is short circuited for some time, and then this voltage is being measured. So this is S1 switch, this is S2 switch. So S1 switch is on for some time. First step, S1 switch is on for some time. S2 is off. Then second stage, S1 is made off and S2 is also off. Then third stage, S1 will remain off, S2 will be on for some time. Then fourth stage, S1 is off and S2 is also off, and then the voltage is measured. So here, this normally it is given in a graphical form. To give the application of voltage in a graphical form. So here this voltage is been applied for some time. This S1 is on, then both are off. Then this voltage is measured over here. So voltage will going to have a variation with respect to time. So some T1 time voltage is been applied. T1 time S1. This is the S1 first component. This is the second, third component, and this one is the fourth. This is the fourth component, and both are off. And both are off. We're going to have a voltage waveform like this. So now this check the moisture level on this insulating material. So if you're going to have a moisture level, you're going to have a different shape of this one. So this peak position is going to vary depending on the moisture level. In case of PDC one, PDC circuit and component is same. Polarization and depolarization current. Polarization and depolarization current measurement. In polarization current measurement, going to have the test sample, going to have a DC voltage source, we have a switch, but here instead of voltage measurement, measure the current. Measure the current over here. So, and here also you can have one switch. So this is the test sample. So this is S1, this will be switch S2, this is one. So S1 is on. That time some current will flow through this micro ammeter. So that is been measured. So this is just a polarization current. This is just since you are applying a DC over here, so it will going to get charged to some. So current will not continuously, not DC. So this is the DC voltage. Irrespective of the equipment applications, the DC voltage is applied. It is just checking the condition of the insulation. On the transformer, to check the component wise insulation, core, magnetic path, and conductor. Out of that, Insulation is the more weakest part of this one. So insulation condition monitoring is done rigorously. So in fluorescent and defluorescent, this current is the first one. This S1 is on and S2 is off. That time this current is the polarization current. First cases. The second cases S1 is made off and S2 is made on. That time current is, so this will be made off and this will be made on, this will be made off. That time this will go to discharge. So you can say charging and discharging current. This the polarization depolarization current also can be called as a charging and discharging current. It is a charging current initially and finally it is a discharging current. Discharging current also. So some voltage will be stored here, so it is going to have a discharging current. So by checking that charging and discharging current pattern, also condition is being measured. So these are the one more technique of this one, polarization and depolarization current. So this all together, these are the few more techniques related to the condition monitoring of class 1. Okay, so now if you have any question, then ask.
Yes, sir. Some questions from the participants.
Yeah.
So it is on screen.
Does the space charge governs the PDs? If so, in what capacity the accumulation of space charge observed at interface site within transformer found between insulating paper and oil leads to PD. Say space charge will not directly say. I shown you the ACDC part of it. If you talk about the charges on these cases, space charges, that is not going to create the voltage level of some kilovolt. Whereas normally insertion voltage is coming out to be in the order of kilovolt. So even if you have a certain amount of space charge on that interface, that hardly is going to raise the voltage to some extent. I will take again the help of the board to answer your question.
Sir, screen. Are you presenting it on screen, sir?
Yeah, I'll just share one.
Sir, kindly share the screen.
Yeah, just use.
Yes, sir.
So, what is going to happen over here? If this is the insulating interface, right? If this is the insulating interface, so this is the press board, this is the oil, and voltage is being applied over here, and PD is going to occur somewhere over here. Now, irrespective of the polarity, if there is a space charge on this particular part, on this one, that is because of this one, while oil and press board interfaces, this is not going to create a major voltage differences. This is not going to create a major voltage difference. The space charge is not going to create a major voltage. It is not a DC situation. It is a AC situations. AC situations will be this one happening. Now, say for example, if you can check the HVAC DC in both the cases, this partial discharge will occur in the prevalent voltage, and this is normally coming out to be at the voltage level, not this applied voltage. I am talking about the gap voltages. Gap voltage will come around the basis of 3 kV on this zone, and beyond that, it should be greater than 3 kV of this gap voltage. So applied voltage will be depending on the total insulation structure. Applied voltage will be according to this one. So in one gap, if it is can attain a 3 kV voltages, it's going to have a breakdown. Then it's going to create a PD insertion. Right? So an applied voltage will be much more than that one. Applied voltage will be much more than that one because it has to be divided somewhere over here and somewhere over here. That way, now the space charge, it will not going to affect this 3 kV. Space charge, if it is sufficient to affect this 3 kV, then you're going to have a variation. So whatever will be minor variation of this induced voltage or voltage created by space charges, or reduction of the voltage or enhance of the voltage with the space charges, that is going to affect that.
Okay, sir. One more question from the same participants is on screen.
Which part, area, location within the transformer is more vulnerable to PD? Okay, in case of transformer, part wise you can say it is the winding because PD can occur only on the winding. Now, area and locations, if you're going to check it, voltage distribution in the winding, if you're going to see it, voltage distribution in the winding, major voltage distribution, if it is winding is not properly designed, if there is a non-uniform voltage distribution, then major voltage will come into the HV side, terminal side. If winding is designed properly, if there is a uniform voltage distribution, then you're going to have the similar chances in all the zone. If there is a not properly designed, if there is uneven voltage distribution, then the HV side is more prone to have the PD. Otherwise, all zone is same because it is the turn to. Again, I will take the help of this board to explain your question. Say, if you consider one winding over here and voltage will appear between this turn to this turn because there will be some insulation over here, turn to turn insulation. There will be some insulation over here, turn to ground insulation, this phase to ground insulation. There will be a core over here. This is sufficiently made it because there is a certain space is provided and this is capable. These insulations from one disc to another disc. Now, each turn is going to have the same voltages. Each turn is going to have the same voltages. So turn to turn voltage will not going to, if this is the one and if this is the one, they are going to have the same voltages. If this is, there is a fault over here. Say this is the first turn and second turn. This is the 20th turns and 21st turn, right? So here, if first turn and second turn, what will be the voltage, and 20th turn to 21st turn, we are going to have the same voltage. Or first disc to second disc, what will be the voltage? 20 to 21 disc, we are going to have the same voltage if it is uniformly distributed. If the design is not proper, if it is not properly done, but you can have a higher voltages between these two turns than these voltages. So this is going to have equal vulnerability in all the insulations. Wherever you're going to have a basically one more thing you can understand it. It is not the voltage will decide the breakdown. It is the voltage gradient which will decide the breakdown. Voltage gradient will decide the breakdown. See, if the voltage gradient is same, then you will have the similar.
One more question, sir.
Okay.
Is on screen.
Failure of transformer due to insulation failure contribute to what percentage? What percentage of? Means you want to mean failure of transformer due to insulation failure contribute what percentage of amount? Means out of the total failure you want to check it. So here this is amount. What I understand from this question is that if there is 100 failure of a transformer, out of this insulation failure is how much percentage? So you can see if there is a major failure is coming in the oil TC. In transformer failure, if you're going to check it, major percentage of failure shared by the oil TC, and that is a mechanical type failure, not by any electrical one. That is either their movement failure and so on. So that is the highest percentage, OLTC, oil tap changer failure. Tap changer to next failure is the insulation. So I can say in overall there is a only two type failure. Conductor failure is a rarest to rarest happening. If that is happened to a conductor failure, then it is also initiated by a insulation failure. Insulation failure was there, it is overlooked, and that leads to a conductor failure. Means the burning of the total conductor. So that is total short is done, and insulation is first burned, and that leads to the burning of the conductor. Right. So here, percentage-wise, if you get it exact figure that I don't have, but overall it is like that. That major failure of the transformer is because of the VLTC failure, and next to it is the insulation failure.
Okay, sir.
Any more question?
Yes, yes, sir. Uh, which harmonics pass through in the transformer from the participants? Which harmonics pass through in the transformer?
With harmonics,
Pass through in the transformers.
uh, can you explain this question? I say harmonics pass through the transformer means
Can harmonics
say
pass through in the
transform.
transformer? Yes.
Say this is what I will talk it in. This is a different way of this one. What we learn in a transformer that if the transformer has a delta one, then harmonics will die out. Is they want to mean that question, or if it relevant to that one, then can be talked that way. That if there is a triplet harmonics, if it is a delta connected or star neutral type transformer, then triplet harmonics will die out on the transformer. That will not going to pass it. So other than the triplet harmonics, all will go through the transformer. If it is don't have the delta connection, then it will going to generate it. So this is a bit of different aspect of it. It is basically from the transformer itself is an active component, and transformer is thought as active component of harmonic generation. Transformer is also active component of harmonic generation. We normally talk about the power electronic devices for harmonic generation, but transformer is also, if it is a saturated mode, it operates, then transformer also will create harmonics. Transformer also will create harmonics.
Okay.
Right? So that is the different part of it. So only triplet harmonics will die out only if there is a delta configurations in some zone.
Yes, sir. One more question. Does the continuous presence of space charges accelerate the aging process of insulation, and would it reduces the degree of polymerization subsequently?
Continuous presence of space charges.
Yes, accelerate the aging process of insulation, and would it reduces the degree of polymerization subsequently?
Degree of polymerization, say aging process, if you know it, there is a team is doing the aging of any insulating material. We call it as a team. In high voltage engineering, we call it team is doing the aging process, any insulation. Team, again, I will take the help of the board because to understand what is team, it's a team effect. Uh, just a minute. Aging process is a team effect. what is called that one? Any insulation aging is a T. T is a this there is a thermal stress, it will going to age it. If there is a electrical stress, it will going to age it. If there is a ambient stress, that will going to age it. If there is a mechanical stress, is going to age it. So if there is a mechanical stress, so this is the 4 responsible agent for the aging of any insulating material. Electrical stress, if it is going to add it, it will going to age it. If there is a temperature, it's going to. Ambient effect is normally that one. If you can see that one insulating material is a fresh one, you bring it and keep it for a long time. Neither you have increased the temperature, nor you have increased the electrical stress, neither you have put any mechanical stress. But still after some time, it will going to age it. That is because ambient effect, it is by the cosmic radiation. Cosmic radiations is going to create it. Now, if the space charge is going to add the electrical stresses, space charge is going to add the electrical stages, so there will be effect on it. Now, normally, the how much voltage is been, how much electrical stresses is been added by the space charge, that you have to check. One insulation, if it is traced by say 5 kV, and one insulation, if it is checked by 5 volt, naturally you can understand it, these insulations will have a more aging. This stress is more. You can 5 volt is there, but say it will age it not only by the voltage stress, then it will age by the ambient stress. If it is a design is such a that it is there is some mechanical stress, that is going to age it. So that is space charge. If it is adding the electrical stresses, then it will going to have a aging.
Okay, sir. No more questions. Okay, sir.
Okay.
Nikul sir, your mic is yes. Nikul sir,
Yes,
yes.
Now, okay, I am visible.
Yes, sir. Yes.
Yeah.
Sir, behalf of Sri Swami Atmanand Saraswati Institute of Technology, we are really thankful to you for spend your valuable time with us. And sir has nicely delivered in the field of conditioning monitoring on transformers. And sir, you have covered the many topics which are really useful for the researcher. And
Okay,
some
thank you.
participants in this STTPs are also going for the research, and I hope the particular STTP is really helpful to those people. Thank you, sir. Thank you very much once again for accept our invitation. Thank you.
Okay, thank you.
Thank you, sir. We will end our session here. Thank you so much.